morning, one and all. Myself, Sreevani, working as an assistant professor in the Department of ECE in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So, in the today's lecture, we are going to learn one of the topic in magnetostatic fields, that is inductors, followed by inductances and magnetic energy. So, before going to discuss about this magnetic energy, we just revise what do you mean by inductor, then how many types of inductances are there, then we are going to learn magnetic energy. So here, firstly, what do you mean by inductor? So inductor is a conductor which carries some current. Means now to produce the inductance, we just consider here a circuit which is acting like a closed conducting path, a carrying current I produces a magnetic field B which causes a flux phi. It is nothing but close integral S B dot ds to pass through each turn of the circuit. So we just consider one simple example for the inductor is an electrical coil which is to be operating with the help of externally applied voltage P. Because of that there exists induced current in that coil. Then because of that induction there exists mutual interaction exists between the coils, and each turn of the coil will produce the current which is producing in a circuit. Means a circuit, it is considered to be a closed conducting path. There is a difference between a circuit and a network. Means a network is said to be interconnection of components and a circuit is said to be, if a network contains at least one closed path, then it is said to be a circuit. Hence, a circuit or closed conducting path, a carrying current I produces a magnetic field B which causes a flux, that is psi equal to integral S B dot ds. Where flux notation is given by psi and it can be measured in Webers. Why? Because magnetic flux can be measured in Webers, and B is said to be here magnetic flux density and it is measured in Weber per meter square. Right? Flux passing through any given area is given by flux density, and magnetic flux density is denoted with B and it is measured in Weber per meter square. So magnetic flux is given by integral S B dot ds. So in order to calculate the inductance of the circuit, we just consider here if the circuit has n identical turns. Means if you observe in the previous circuit, here number of turns will be more. If the circuit has n identical turns, means number of turns in the circuit is more. Let it be n. Then we can define the flux linkage factor as lambda, nothing but magnetic flux linkage factor as lambda, and it is given by lambda equal to n psi, where n is said to be number of identical turns in the circuit and psi be the flux through each turn. And also if the medium surrounding the circuit is linear, then the flux linkage factor lambda is directly proportional to the current I which is producing it. Hence, the magnetic flux linkage factor lambda is directly proportional to the current which is producing inside the coil. Or if we replace that proportionality with a constant, then it is said to be lambda equal to L into I, where L is said to be a constant proportionality and it is also called as the inductance of the circuit. The coil or the circuit is said to be inductor, and the property it is going to exhibit is said to be inductance. So, where L is said to be constant proportionality and it is also called as inductance of the circuit. And the inductance L is a property of the physical arrangement of the circuit. A circuit or a part of circuit that has an inductance is called an inductor. So in general, we can say that inductor is a conductor which carrying some current. Then here, if you consider magnetic flux linkage is nothing but n into psi as equation number 1, and the same magnetic flux linkage, if you are dealing with inductances, then lambda equal to L into psi. Then from those two relations, lambda equal to n into psi and lambda equal to L into I. From these two relations, if you equate lambda and lambda and same, then n psi is equal to L into I. Then from this, L is equal to N into psi by I, where N be the number of identical turns and flux component is denoted with psi, and I be the current which is producing inside the coil. So from equations 1 and 2, we may define inductance L of an inductor is the ratio of the magnetic flux linkage factor as lambda to the current I through the inductor, and that is given by here L is equal to lambda by I, and lambda is nothing but N psi by I. Here lambda is said to be magnetic flux linkage factor and psi be the flux through each turn. Right? Then a magnetic energy means which is stored in an inductor is expressed in a circuit theory is given by Wm equal to half into Li square, where L is said to be inductance of the circuit and I is current which is flowing through that coil. Then from these two energy considerations, if you find the equation for L, then L is given by 2 into Wm by I square, where Wm is the magnetic energy in the inductor. Thus, the self-inductance of a circuit may be defined or calculated from the energy considerations, and it is given by L is equal to 2 Wm by I square. If instead of having a single circuit, means from these two analyses we have got L is equal to N psi by I, and from the energy considerations L is given by 2 Wm by I square. Means if you have only one single circuit, the circuit itself provides an inductor, then it is said to be self-inductance. Suppose instead of having a single circuit, so if you have two circuits and which are carrying respective currents as I1 and I2, then there exists a magnetic interaction between the two circuits. Because of that, there are 4 flux components need to be produced, and those 4 flux components are given by psi11, psi12, psi21 and psi22 are produced, where psi11 is said to be a flux which is generated in the circuit 1, and psi22 a flux generated in the circuit 22, whereas 1, 2 and 2, 1, because of that there exists mutual interaction between the two circuits. Because of that, mutual inductance is going to produce. Right? So here is the example for the circuit which are having two different circuits, circuit 1 and circuit 2. So in the circuit 1 we have the current which is flowing through the circuit 1 is I1, and in the circuit 2 it will be given by I2, and to produce the current in the coil we need to apply some external voltage or external field. Because of that there exists mutual interaction between circuits 1 and 2. So psi11 means because of this interaction there are 4 flux components need to be produced, that is psi11, psi12, psi21 and psi22. So psi11 is related to the only circuit 1. See, means in the circuit 1 itself provide the flux, and it is given by L1 also, self-inductance. And psi22 is also produced in the circuit 2, that is because of that circuit 2 itself. So psi11 and psi22 are sometimes said to be self-inductances of the circuits, and psi12 and psi21 are said to be two mutual inductances, and because of that mutual interaction between the circuit 1 and 2, these two flux components are to be produced. Right? So the flux psi12, for example, in order to calculate in order to write the mathematical equation for the flux component for psi12 or psi21, let it be, for example, if we consider psi12, then the flux passing through the circuit 1 due to the current I2 in the circuit 2, psi12 flux producing in the circuit 1 due to the current I2 in circuit 2. Suppose if we are considering another flux component as psi21, means the flux passing through the circuit 2 due to the current I1 in the circuit 1. So if B2 in the field due to I2 and S1 is the area which is occupying in the circuit 1, then psi12 can be written as integral S1 B2 dot ds. Suppose from this we can write the equation for psi21 means integral S2 B1 dot ds. Means flux producing in the circuit 2 due to the current I1 in the circuit 1 and the field B1 is said to be due to the I1 and in the S2 area of the circuit 2. So then psi 21 is equal to integral S2 B1 dot ds. Similarly, if you want to write the equation for psi 12, then integral S1 B2 dot ds is given by these are the two flux components which are produced in the circuits 1 and 2, and these two are said to be mutual inductances. So to write the equation for mutual inductances, we just consider here mutual inductance definition. That is, in order to define mutual inductance, we just consider the notation for mutual inductance as M, and that is between 1 and 2 denotes 1, 2 as the ratio of the flux linkage lambda 1, 2. Means that is given by lambda 1, 2 equal to n psi. Previously we have defined that flux linkage factor lambda is equal to n psi. So lambda 1, 2 we can consider, hence that n1 into psi 1, 2 on the circuit 1, 2, circuit 2. Suppose we want to define it as lambda 2, 1 means which is equal to n2 into psi 2, 1 means on circuit 2, 2, circuit 1. Right? So from this lambda 1, 2, we are going to consider here mutual inductance M12 is equal to, and we have considered self-inductance as it is the ratio of the magnetic flux linkage lambda to the current which is producing in the circuit is given by self-inductance, that is L is equal to lambda by I. So lambda 1, 2, we are defining here mutual inductance for M12. Hence, it is the ratio of lambda 1, 2 to the I2. So, and here, in place of this lambda 1, 2, if you substitute N1 into psi 1, 2 by I2, then for the mutual inductance, M12 is given by N1 psi 1, 2 by I2. Similarly, the mutual inductance M21 is defined as flux linkages of the circuit 2 per unit current I1. Hence, it is M21. So, M21, similar to that of this, M21 can be written as lambda 21 by I1, which is equal to N2 into psi 21 by I1. Alright? So, where M12 and M21 are said to be mutual inductances of the two circuits. Right? So, M12 is the ratio of the flux linkage factor lambda 12 is given by N1 into psi 12, whereas M21 can be given by it is the ratio of the lambda 21 to the I1, where lambda 21 can be given by N2 into psi 21 by I1. Okay, then inductors and inductance means if you want to find the relation between self and mutual inductances, then mathematically those two can be expressed as, it can be shown by using energy concepts that if the medium surrounding the circuits is linear, means in the absence of ferromagnetic materials, then it is given by M12 equal to M21. Means if the circuit is to be satisfied the linearity property, it has to obey the homogeneous property. Means the mutual interaction between the 1 and 2 will be similar to that of 2 and 1. Hence, M12 equal to M21. By this relation, we can say that mutual inductance M12 or M21 is expressed in henries and should not be confused with the magnetization vector M expressed as ampere per meter. So here magnetization, which is given by M, is the notation for that, similar to that of polarization in electrostatic fields. Here in the magnetic fields, that is vector is given by magnetization vector and it is represented with capital M. And we define the self-inductance of the circuits 1 and 2. So previously we have considered the mutual interaction between the circuits 1 and 2. Because of that, the two mutual inductances we can define it as M12 and M21. Now we are going to define self-inductances of the circuits 1 and 2 separately as for L1. Self-inductance in the circuit 1 is given by lambda 11 by I1, which is equal to, where lambda 11 is said to be flux linkage factor which is produced in the circuit 1 itself. So L1 equal to lambda 11 by I1, which is equal to N1 into psi 1 by I1, where N1 is the number of turns in the circuit and flux producing in the circuit 1 and the current which is generated in the circuit 1. Similarly, now to write the self-inductance for the circuit 2, we just consider here L2, and is nothing but lambda 22 by I2. So for the if you want to define the self-inductance for the circuit 1, here L1 is given by N1 into Psi1 by I1. For the same analysis, if you apply for the circuit 2, it will be given by L2 equal to lambda 22 by I2, which is equal to N2 into Psi2 by I2. So here L1 and L2 are the two equations are said to be self-inductances of the circuits 1 and 2 respectively, where flux components Psi1 is produced in the circuit can be considered collectively as with the Psi11 and Psi12. So flux producing in the circuit 1 itself is given by Psi11, and the flux producing in the circuit 1 because of the current I2 is given by Psi12. And similarly, in order to write this Psi2, flux producing in the circuit 2 itself is given by Psi21 plus Psi22. Circuit 2 itself providing the flux component as Psi22, and the mutual interaction component is between 2 and 1 is given by Psi21. Right? So based upon this Psi1 and Psi2, 4 flux components we have considered, that is Psi11, Psi12, Psi22 and Psi21. 1 and 2 are flux components which are producing in the circuit 1 and 2 respectively, and 1, 2 and 2, 1 are the because of those two components are existed because of their mutual interaction between the circuits 1 and 2. Right? So next is the total energy in the magnetic field. So just now we have seen how the self and mutual inductance need to be produced in the circuits 1 and 2 as separately. Now we are going to consider the total energy which is produced due to L1, L2 and mutual inductances as Wm is given by W1 plus W2 plus W12. Energy produced in the first circuit, and this is for second circuit because of the mutual interaction, that is given by 1, 2 or else 2, 1. So identically these two are equal. Just now we have considered in order to obey that linearity property, their mutual interactions are same, hence M12 equal to M21. Because of this, we just consider here collectively one component as W12. And if we substitute W1 by energy equation, W equal to half into Li square. So if you want to consider it for the circuit 1, circuit 2 and the mutual interaction between the circuits 1 and 2, then we'll have here Wm equal to half into L1 into I1 square plus half into L2 into I2 square plus M12 into I1 into I2. This is plus or minus M12 means we just consider in place of this M12, we consider M21 or also there is no change in the equation. Right? So the total energy which is present due to the total magnetic energy which is present due to L1, L2 and M12 or M21 is given by here Wm equal to half into L1 I1 square plus half into L2 I2 square plus M12 into I1 I2. Right? So half into L1 I1 square is for only circuit 1 and L2 I2 square is only for the circuit 2, where exists this M12 is between either 1 to 2 or else 2 to 1. Right? So L1, L2 are the two self-inductances of the circuits 1 and 2, and M12 or else M21 is the mutual inductance between the 1 and 2 or else 2 and 1. So the positive sign is taken if the currents I1 and I2 flow such that the magnetic fields of two circuits strengthen each other. Hence we have considered the positive sign here. Or if the two currents are such that the magnitudes are opposite to each other, that is the case, we just consider the negative sign in between them. Right? So an inductor is a conductor. So the general definition for an inductor is it is a conductor arranged in a shape appropriate to store a magnetic energy. So similar to the capacitor, here also inductor is a conductor which is able to store magnetic energy in the form of currents. Is said to be an inductor. Right? So in order to calculate this internal inductance and external inductance, and we know that the relation between time constant as RC with the help of rearrangement time or relaxation time. We just consider here in an inductor such a coaxial or parallel wire transmission line. Example for that we have considered here coaxial cable or parallel wire transmission line. The inductance produced by the flux internal to the conductor is called the internal conductor, inductal, internal inductance, that is denoted with L in, and while that it is produced by the flux to the external to the circuit is called the external inductance and it is denoted with L external. So the total inductance L is given by due to the internal along with the external, that is L is given by L internal plus L external. Then we know that for the capacitor, as we have discussed in the electric fields, that is rearrangement time or relaxation time, this RC is to be obtained as epsilon by sigma. How we have got already, we know that generally R is expressed as it is the ratio of V to I. If you want to express the voltage and current terms in the electric fields, that is given by minus integral L E dot dl is the equation for V, and I is given by integral S J dot ds. Then J is said to be here current density. If we express this J in terms of electric fields, that is minus integral L E dot dl by J is given by according to the conduction current density sigma into E. Then integral S E dot ds is the equation for this R. Similarly, the general definition for the capacitance is given by C equal to Q by V, means charge of one of the plates in the parallel plates, and V be the potential difference between the two parallel plates, and it is given by, if you want to express this Q in terms of electric fields, that is integral S D dot ds by V minus integral L E dot dl. Then as we know that the relation between D and E is given by epsilon into E, then epsilon might be a constant, then integral S E dot ds by minus integral L E dot dl. Then to get the time constant, relaxation time or rearrangement time, we need to multiply these two. Hence, if you multiply R and C, then you are going to get minus integral L E dot dl by sigma integral S E dot ds into C value epsilon integral S E dot ds by minus integral L E dot dl. So this E dot ds, this E dot ds and E dot dl gets cancelled. Hence RC equal to, and minus gets cancelled, epsilon by sigma is the resultant. So this is the way we have learned the relaxation time or rearrangement time in electrostatic fields. In the similar way, if you multiply L and C here, we are going to get mu and epsilon need to be generated. Right? So this is the way inductor in self and mutual inductance need to be developed. Then after that, magnetic energy. So in order to derive the magnetic energy equation, we need to know first of all how the electric energy is derived in the electrostatic fields. So the potential energy in an electrostatic fields is given by WE. E stands for electrostatic fields and the energy denoted with W. So WE equal to half integral V D dot E dV, where D and E both are vectors, where D is said to be electric flux density and E be the electric field intensity. In a volume integrals, the energy stored in a capacitor can be given by here WE equal to, in the electric fields, 1 by 2 integral V D dot E dV. Or if you want to substitute D by epsilon and E. Why? Because there exists a relation between D and E, that is epsilon into E. So 1 by 2 integral V, if you substitute D by epsilon into E, then by default E is there in the equation, then E into E becomes epsilon into E square dV. Right? So energy stored in an electrostatic fields is given by half into integral V epsilon into E square dV or half integral V D dot E dV. Right? In the similar expression, means in place of D, what is the term which is analogous to D in magnetostatic fields? D is analogous to B in magnetostatic fields, where D is said to be electric flux density and B is said to be magnetic flux density. Right? and E is analogous to H in magnetostatic fields. E is nothing but electric field intensity and H be the magnetic field intensity. So if you substitute in place of D by B and in place of E by H, then we are going to get Wm is nothing but magnetic energy which is stored in an inductor is given by half integral V B dot H dV or half integral V mu into H square dV. Why? Because we know that the relation between B and H is B equal to mu into H. Magnetic flux density is expressed in terms of magnetic field intensity is given by B equal to mu into H. Right? So a similar expression for the energy in a magnetostatic field we are going to derive. So a simple approach is using a magnetic energy in the field of an inductor. So that is given by Wm equal to half into Li square, which is analogous to the same equation in the electrostatic fields is nothing but energy stored in a capacitor is given by half into Cv square. C is nothing but L in the magnetostatic fields, V is analogous to I in the magnetostatic fields. Hence, Wm magnetic energy which is stored in the inductor is given by half into Li square, and the energy which is stored in the magnetic field of the inductor is going to derive the next success. So in order to derive the energy which is stored in a magnetic fields, we have considered one cubical object which is placed in the XYZ directions, X, Y, Z directions, and the three directions differential components are given by delta X, delta Y, and delta Z are the three differential components in the X, Y, Z directions. And if we are placing this cubical object in the XY field XZ field, then differential components need to be identified first. X, Y, Z are the three coordinate system variables for Cartesian coordinate system. Hence, differential components are given by dx, dy, dz. In order to calculate length, we need to consider dx into ax for the respective direction, dy into ay for the respective, dz into az for the third direction. Suppose if you want to calculate the differential surface area, these are all dl. ds if you want to find, suppose I want to consider here z direction, means my z direction component as unit vector as az. Means if the z equal to 0 plane we have considered, means x, y plane we have considered. If x equal to 0 plane means we are going to consider yz plane. If y equal to 0 plane means we are going to consider xz plane. Like this we are going to consider the field components along with the directions. So if you are going to consider it as with the az, then the differential surface area formula is given by dx dy into az. Suppose we want to calculate it along with the y direction, then dx dz into ay. Along with x direction means the differential surface area is given by ds is equal to dy dz into ax. So this is the way we have to consider the differential surface area formulas in the rectangular coordinate system. Similarly, we are going to calculate here volume. Hence, we need to multiply three differential components. Hence, the formula is given by dx, dy and dz for that. Rectangular means we are going to use here three variables as x, y, z coordinate system variables. And this is the thick line we are considered is conducting sheet which is placed in the y direction. Y direction means y equal to 0 direction we are considered. Hence, y-directional component differential surface area is given by ds is equal to dx dz into ay. Right? So let the volume be covered with the conducting sheets. These are the two conducting sheets which are having top and bottom surfaces, and with the currents carrying is represented with delta I. So let the volume be covered with the conducting sheets at the top and bottom surfaces with the current is given by delta I. So this is the delta is representing for the change. Right? So to derive the equation for magnetic energy in the magnetostatic fields, we need to consider that simple diagram. From the diagram, we are going to consider self-inductance. Then after that, we are going to substitute it in the Wm equation, that is nothing but half into Li square. So for a changes case, we just consider here del Wm is equal to half into delta L into delta I square. Right? So to calculate this delta L, delta I, we just consider here from the figure delta L means from self and mutual inductances, we have defined self-inductance L is it is the ratio of the flux component to the of current which is producing in that coil. So change purpose we just consider here delta L which is equal to delta psi by delta I. Then psi means in general we know that psi is expressed, magnetic flux is expressed in terms of flux density means integral S B dot ds. Flux density is given by B and flux psi is denoted with magnetic flux is denoted with psi. So if you want to find this one means we want to find differential component of this d psi means consider both sides differentiation that gets cancelled, d psi becomes here b dot ds. And b can be measured in y direction means the formula for ds is given by dx dz into ay. And b can be expressed as by into ay. Right? So from the figure we have considered the magnetic field is along the y direction, hence this d psi is given by here b dot ds. And we know that the formula for that b is mu into h and ds is dx dz into ay dot ay. So the dot product representation of two same unit vectors result is 1. Then based upon that we are going to get mu h into dx dz is given by here d psi. So for a differentiation purpose we use d psi is equal to mu h into dx dz as the formula which we have got. Now for a small change case we have considered here self-inductance is denoted with delta L and which is given by mu h into delta x into delta z by delta I, where delta psi formula is given by mu h into delta x into delta z, which is similar to that. This is the analysis. Right? Consider this as equation number 2. And we know that from this magnetic field intensity means I equal to h dot dl. We know that from the Ampere circuit law, that is integral L h dot dl is equal to I enclosed. That I enclosed is replaced by a change case. Then we have considered delta I and h is along with this one. We have considered the change for the direction is h into delta y. Hence, delta I is equal to h into delta y. And this we need to substitute here then to get energy density equation. Right? So, in order to derive that equation, we are going to consider then delta m equal to, as we know that the magnetic energy formula half into Li square, then half into delta L into delta I square. We know that delta L formula is mu h means I'm going to write here del Wm is equal to half into delta L means mu h delta x delta z by delta I is the value of delta L. Then delta I square is nothing but in place of delta I square if we substitute h into delta y. Delta I square is nothing but h square into delta y whole square. Right? So, in order to get or then in place of this delta I, if we substitute h into delta y here, then already by default we have in the equation delta x into delta z is there. Then if you want to multiply this one with delta y, then the volume is obtained as del v. So half into mu h square into delta x delta y delta z is to be obtained. Or in place of h into delta y, if you consider it as this one delta I, then delta x delta y delta z 3 if you multiply that the formula is given by volume is differential volume formula in the rectangular coordinate system is given by dx dy dz. Right? So the multiplication of these three factors delta x delta y delta z becomes delta v, and half into mu h square. Then from this del Wm equal to half into mu h square into delta V. Or instead of considering that del Wm, we just want to derive the equation for del Wm. So the magnetostatic energy Wm is defined as here Wm equal to limit del V tends to 0 del Wm by del V. So del Wm means previously we have got 1 by 2 mu h square into del V, and this del V gets cancelled, 1 by 2 mu h square into delta V by delta V. So this is the value which is given by del Wm, and this gets cancelled. Remaining is half into mu h square is to be obtained. Right? So Wm equal to half into mu h square, or in place of mu h, if you consider it as B, then half into B dot h, or in place of h, if you want to substitute B by mu, then means we have three relations as to be obtained. That is, in general, B equal to mu into h, or h is given by B by mu. So instead of considering B, if you consider h, then in place of h, if you substitute B by mu, already B is there. B into B becomes B square by 2 mu. Right? So in three different ways we can express the formula for magnetic energy is Wm equal to half into mu h square, nothing but half into Bh or B square by 2 mu. So thus the energy in a magnetostatic field in a linear medium is given by Wm equal to integral V Wm into dV, or simply we can say that Wm equal to half into integral V dot h dV, or half into integral V mu h square dV. This is the finalized equation for the magnetic energy which is stored in an inductor. Right? The similar analysis which we have learned in the case of electrostatic fields, that is energy stored in a capacitor is given by, or in the electrostatic fields it is given by half into integral V d dot E dV, or 1 by 2 integral epsilon into E square dV. As we know that D is analogous to B and E is analogous to H in magnetic fields, we just replace D by B and E by H, then magnetic energy equation is to be obtained as half into integral V B dot H dV, or half integral mu into H square dV. Right? So in this lecture, what we have learnt is introduction to inductors and two types of inductances we have discussed, self-inductance and a mutual inductance, followed by magnetic energy which is stored in an inductor. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.